Okay, so we just talked about rain shadows, and we talked about expansional cooling on the windward side and compressional warming on the leeward side. And in doing so, we're comparing the vertical temperature profiles of the parcel to the vertical temperature profiles of the dew point. And I want to take that a little bit farther in talking to you about predicting climate through rain shadows versus predicting day-to-day storms through soundings. So to predict storms day-to-day, you need soundings. This is just from Tropical Storm Faye that was in July of 2020. So you need soundings to do that. You may think you only need radar. Soundings are critical as well. And in some ways, there's no way the radar would work well without the soundings, and the soundings can work better with the radar. The point about the soundings is that you can tell whether or not that parcel is going to rise just over the mountainside and then sink and compressionally warm, or is that parcel going to rise on top of the mountainside and keep rising and keep rising and keep rising to form a huge thunderstorm cloud. One of the ways you can do that is through the sounding to see whether or not you're going to have a parcel that rises perpetually up to the stratosphere, potential tornado, or if it sinks and it's a potential thick fog. What we're introducing here is the idea of stability in the atmosphere. This is a atmosphere where the parcel continuously rises is an unstable atmosphere. The atmosphere where a fog sits down on top of the surface is a stable atmosphere. Let's go into what the specifics are in what happens next, rising or sinking. To look into this, we have to go back and review the second law of thermodynamics, which says that all systems tend to move toward equilibrium. Equilibrium in energy, equilibrium in temperature. This is an equilibrium in temperature. And what I want to talk to you about is the idea of stable equilibrium versus unstable equilibrium. You can think about a gymnast when you think about this. Let me move this up so you have a little bit more to read. A gymnast on the uneven parallel bars will hang down, and if her coach pushes her, she will come right back to original hang down position. That is a stable equilibrium situation. A pendulum is a stable equilibrium situation. You push the pendulum, it comes right back and back and back, and it finds equilibrium right where it began. Unstable equilibrium is like the gymnast who's doing a handstand on top of the uneven parallel bars. If you nudge that gymnast one way or the other, there's no way that she's returning to that original position without an awful lot of energy. So what we're looking at is an equilibrium position that is either stable or it's unstable and can keep going. For instance, if she were nudged in one direction, she would go all the way around and probably keep going. If she went back and forth like a pendulum, she would not come back to her original position in the handstand. That's an unstable equilibrium where she is up here, because if she moves, she's going to keep going and she'll never come back to her original. That's the best I can give you in terms of an analogy there. How does that refer to an atmospheric situation? Well, if you nudge a parcel, will it sink or will it rise? That's what we're looking for in the sounding. So in other words, if you're looking at a stable gymnast and a stable environment, what you're saying is if you nudged up the parcel holding that fog, would the fog lift and continue to rise, or would it sink? And I think you know the answer to that. that even if you forcibly lift that fog, it would sink back down again as soon as the nudge goes away. The reason being that the fog is there because it's cooler than the atmosphere itself and it cannot rise. If you lift it up and nudge it, it's just going to fall right back down again as soon as the nudge is gone. It's less buoyant. On the other hand, what's an unstable equilibrium in the atmosphere? We know what it is with a gymnast. With an atmosphere, the unstable equilibrium is the storm cloud that's just hanging on top of you. If a wind comes along and nudges that cloud, you could definitely have this downburst, which is over Phoenix. It's pretty impressive, I think. So as soon as a little bit more energy hits a atmosphere in unstable equilibrium, it will produce a result that cannot return to the original position at all. That's an unstable atmosphere. To go over it specifically, this could be nudged by a wind or by wind from a frontal lift. We'll get into that soon. It can cool even further. It can condense even further, release just a bit more heat. Then all of a sudden that temperature of the parcel is greater than the temperature of the environment, and it keeps climbing up. When those rain droplets get too big and there's a little bit more burst of energy, they all can come back down again. So this is what we're referring to as an unstable atmospheric equilibrium. We're going to get into the mathematics of it in a second. Let's go into, just review, you know now that low clouds are generally in a stable atmosphere. And clouds with vertical development, we're talking about an unstable atmosphere that lends itself to that. And we are comparing the temperature of the parcel to the temperature of the environment. The temperature of the parcel is in yellow on a sounding. The temperature of the environment is in red on a sounding. So here's your sounding. And you see your temperature of the environment starting here right with the temperature of the parcel. And then we see the two different tracks it takes. Remember, the parcel is assumed to be dry. That's why it's climbing at a different rate by our calculations than the observed temperature of the environment from the balloon. All right? When we are looking here, you are assuming that the parcel is dry. You are assuming that the parcel has some lift underneath it to get off the ground. The lift can be convective, the lift can be frontal, or topographical, or convergent. You're assuming that it has some lift. And you're assuming that it starts its journey using the dry adiabatic lapse rate right here. After it condenses, which is when the dew point meets our calculated parcel temp rate right here, after that, it will climb at a moist adiabatic lapse rate. Now, you might have a hard time seeing it here, but this lapse is a bit gentler than the lapse above it, which is a bit steeper. It's hard to see in here because we don't have much room. So this is a dry adiabatic lapse rate, and what this is a laid down low rate. Remember, it's a little bit more shallow. And this is a moist adiabatic lapse rate, which is a little steeper, a little stand-up straight rate. The big question is, what will happen to this cloud once it's condensed? Will it rise or will it hang out there? And that's where you get to do the predictions. Just to go over, this is how we lift a parcel off the surface. That parcel is lifted. We use the sounding to find out if the parcel is going to hang out at one altitude or is the parcel going to continue to rise up. And in doing that, let's go back to our sounding stories and our stand-up straight lapse rate story, which was about the guy who gets up, meteorologist who gets up in the morning and it's cold out there, and he notices that there's a thick layer of fog under his area. Tells you a lot right there. Tells you that it's the morning, that it's cold, that he is on top of the hillside, so probably that parcel was lifted by topographical lift, and it's settled down without rising. So when you think about that story and that stand-up straight lapse rate, you can also think about the fact this is a stable atmosphere. This atmosphere is promoting fog, and the fog forms right at the condensation level. The condensation level, again, is the point where there's an intersection between the parcel lapse rate and the dew point. We talk about stable atmospheres here. In terms of the parcel that's involved in it, we can use other mnemonics for the parcel. We can say that the parcel temp is stuck underneath the environmental lapse rate in a stable atmosphere. We can say that the parcel stays stagnant in a stable atmosphere. We can say that the parcel makes a stratus cloud, a fog cloud, in a stable atmosphere that stretches out and that stays stagnant. We often think about smog in stable atmospheres. So I hope those mnemonics help you to understand the difference between the stable atmosphere and the actions with the parcel. The parcel is stuck, the parcel is stagnant, the parcel features stratus clouds that stretch out. Another way of looking at it is the parcel is cooler and its volume as a result contracts. When its volume contracts, its density goes up, because remember, density is mass over volume. Volume is in the denominator. If the denominator goes down, the dividend goes up. So this is going to stay low and be stagnant. Great place for pollution to gather. The condensation nuclei in here can really add density to the cloud and keep it very stable so it's hard to move off. That's why LA gets sucked in by smog quite often. The history, the event that really spurned the U.S. to the Clean Air Act was the 1948 killer smog of Donora, Pennsylvania, and their steel mills in Donora. And what was happening was that it was a very, very cold snap in Halloween that sealed cold air over the town. And there was warmer air above that wasn't mixing, because you know the warmer air is not going to drop to mix. So on top of that, you had all of this pollution coming from the smokestacks that was getting trapped in the cold air. It produced a smog that killed in upwards of 60 people in 1948 and really moved us toward the Clean Air Act. Someday I'll give you my story about Taipei and LA, but not right now. To make the atmosphere more stable, you've seen an example of that in Pennsylvania, a very cold snap with warmer air above it. And so what we note here is that if you cool the ground and you warm the air aloft, you are shifting the environmental lapse rate to be in a steeper position. That environmental lapse rate can go from a normal of about 6 degrees Celsius per 1,000 meters all the way to an inverted -5 degrees Celsius over 1,000 meters. I know that the negatives don't seem to make sense. You got to think about it, but keep in mind that the important thing in here is when you chill the ground and heat the atmosphere, you are tilting the environmental lapse rate to a steeper level, and the steeper level can even go over to a temperature inversion. Why don't clouds penetrate the stratosphere? The same reason. The anvil heats the top, the anvil of a thunderstorm cloud hits the top of the troposphere and meets the warmer stratosphere. Once it meets a warmer stratosphere, it can't be more buoyant. So that's why clouds can never penetrate the